So chemical reactions is always accompanied or is always related with chemical change. Okay, chemical change. In a chemical reaction, what are important features or important things that we need to know is we have something called reactants and products. Okay, we have reactants, the one on the left side. These are like single elements maybe, or these are like a combination of elements. A product is the one that takes under the process and form a new substance. That's a product. Okay, so if you have a chemical reaction, you always need to expect chemical change. There's always chemical change and physical change. Just to make, to give you a clear picture, what is the difference between a physical change and a chemical change? If someone says, this is a chemical change. No, this is not physical, this is not chemical, this is a physical change. How do you differentiate that? What's a physical change or what's a chemical change? Let's start with that. Can anybody give me the difference between chemical change and physical change? What do you think is a chemical change?
Chemical change.
Yes.
Chemical reaction conversion substance to another.
Okay.
Change from water or ice into water.
Yes. Yes. For example, if solid ice turns into a liquid ice, a liquid water. That's it. That's a physical change. Chemical change would be hydrogen reacts with oxygen to make H2O. Yes, new substance formed. Okay. If I broke up a piece of chalk into two pieces, is it a physical change or chemical change? It's a physical change. It's really, or if I tear a paper into like 5-6 parts, it's going to be a physical change. It's not going to be a chemical change. Okay. In a chemical change, composition of the substances, composition in which the substance is made, has to be changed. Okay. In a physical change, that composition remains the same. Okay. Well, so when you have chemical reactions, you need to have a chemical equation. Okay, a chemical equation is simply it is an expression that tells you reactants are changing into products. In other words, what the reactants constitutes the starting materials in a reaction and what products are formed. Okay, that is. How do we explain this? By having a chemical equation. A chemical equation is an abbreviation for us, or it is a statement to show there takes place chemical reaction. Okay, chemical reaction. Here we have a chemical equation. CH4 reacts with oxygen. CH4 is a main component of a natural gas. It's a gas that we are using in our daily life, in our house, for example, or in the lab. Okay. CH4, it's called methane, reacts with oxygen, and new products are formed. What are they? Carbon dioxide and water. Now, when you write chemical equations, there is one important, there is one important feature that we need to know. That is, regardless of any chemical change you have, the quantity has to be remains the same. In other words, let's say you have CH4, X amount of CH4, you have Y amount of oxygen, and when they combine together, you get carbon dioxide and water. A new substance is formed, new products we got, but in terms of quantity, they have to remain the same. How do we show this? We show this by using coefficients, for example. These numbers are said to be coefficients, okay? The numbers that we are using here are coefficients. So we make sure that the equation has to be balanced. Balanced means whatever atoms or whatever molecules you have on the reactant side, you have the same on the other side. If you do that, then the equation is what? The equation is balanced, okay? And do you remember what law is supported balancing equation? The law of, when we discussed about chapter 2, that is called Dalton atomic theory. That's called the law of conservation of mass. The law of conservation of mass. What does the law of conservation of mass tells you? whatever atoms or whatever molecules you have on the reactant side, the same atoms you have on the product side. Okay, that's called the law of balancing equation. Actually, that is also the law of conservation of energy. Remember last week when we discussed about the law of conservation of energy, we said that heat lost or heat gained by a substance is the same as heat lost or heat gained by the other substance, because if iron, for example, if I heated iron on a water, and the hot iron, if I take the hot iron to the cold water, what happened to the cold water? The cold water is warms up, right? And the hot iron is lose heat, right? How much heat the hot iron lost and how much heat the cold water gained, they have to be balanced, they have to be equal. Okay? That's called the law of conservation of energy. The law of conservation of energy is the same principle we have the law of conservation of mass here. We show the law of conservation of mass by using coefficients here, by using balancing the equation. So balancing the equations are very important. Reactants are written on the left side. These are reactants. The products are always written on the right side. These are the products here. And coefficients, these are the numbers. Coefficients show the number of molecules, a given element or a compound that reactor forming. These are the coefficients here. What is the coefficient of carbon dioxide here? Huh? The coefficient of carbon dioxide?
1.
1. It's not 2, it's 1. What is the coefficient of CH4?
1.
It's 1. It's 1. Okay? Now, many times, many of us made a mistake. When you balance the equation, please don't touch the subscripts. These are the subscripts here. These are the subscripts here. This is the subscript here, and this is the subscript. You don't touch the subscripts. If you touch the subscript, what happens? You're changing the substance. You're changing the identity of the element. Okay? So you always play with the coefficient to balance the equation. You can do whatever you like in the coefficient, but don't ever touch the subscripts. Subscripts. Make sense? Okay. Okay. Yeah. Yes. Go ahead. Yes.
You said don't touch the
subscripts.
The 4 and the 2.
The 4 and the 2, the
Yeah.
2 and the 2 here. Yes.
Oh,
But we can play. If you want to balance the equation, for example,
Did they split the 4 over there?
I'm sorry.
Did they split the 4 over there?
Yes. You see, for example, how many hydrogen you have here? 4, right? How many hydrogen you have here?
4.
4. Because 2 times 2 is 4. How many oxygen we have on the product side? How many oxygen we have on the product side?
4. Sorry. 4.
4. We have 4. 2 oxygen here, 2 oxygen here. These 2 is used for hydrogen and at the same time for oxygen. We have 4. Okay? How many oxygen we have here? 4. How many carbon we have here?
1.
How many carbon we have here?
1.
See, so the equation is balanced. This equation is balanced. Does that make sense? Is everybody clear now? Right? The equation is balanced. So we always have to use coefficients, not the subscript, to balance the equation. Now, when you write a chemical equation, you have to also provide informations that it's not enough just to write the chemical equation. You have to write the chemical status of substance, the physical status of substance. For example, the substance that I'm dealing with, solid. I don't have to write solid, S-O-L-I-D, but I use S. It's a common understanding that if I have S, it means solid. If I have L, it means liquid. If I'm doing with gases, I'm writing G, right? If I am doing AQ, what's AQ refers to?
Water.
It's a solution. It dissolves in water. It's a substance that dissolves in water. Okay. For example, the difference between aqueous and NaCl, sodium chloride aqueous, and sodium chloride. What's the difference? Sodium chloride dissolves in water. That is called aqueous, because that dissolves. You mix. You add some salt in water right there, and then it's going to be what? Aqueous sodium chloride. Aqueous. aqueous, it dissolves in water. When something dissolves in water, what will happen with the ions? Do you think you have sodium chloride per se, like sodium chloride acids, or it has to be broken down into ions? It has to be broken down. It has to be broken down into ions. What are the ions? Cations and anions. What are they? The sodium ion and what are the two ions that are formed in sodium chloride? Chloride, yes. Sodium ion and chloride ion. Do you know the name of the substance when the substance dissolves in water? What do you call it? If something dissolves in water, like sodium chloride dissolves in water, well, it is aqueous solution. It is also called, it's also called electrolyte. Electrolyte. Electrolyte and non-electrolyte. Okay, I can give you a simple example, very simple example. Can I use it? I'm going to drink it. You have sugar. You have sugar on one side. Dissolve sugar in water. You can dissolve sugar in water. They can be dissolved, right? On the other one, on this one you dissolve salt in water. Salt in water. On this one you dissolve sugar in water. Now, one of them is electrolyte. The other one is non-electrolyte. Okay, which one is electrolyte?
Sodium.
Sodium chloride in water is electrolyte. Which one is non-electrolyte? Sugar in water. What I'm trying, okay, the difference is sugar is organic compound, right? It's not ionic compound. When sugar dissolves in water, it doesn't form ions. You can't have a positive and a negative ions. It is just a solution. It's just a solution. But salt, like sodium chloride or potassium chloride or magnesium chloride, whatever, if it dissolves in water, it forms ions, a sodium ion and a chloride ion. Now we call this electrolytes because they can conduct electricity. Okay? If you put some wires, electric wires, the light comes out. And then if the wires are attached with bulbs, right, you can see lights. For the light, there is something called electric current. Electric current has to transfer from, there's like a circuit from positively charged ions to negatively charged ions. And that happens here. You put in water, wires, two wires, attached with a bulb, you can see the light, just like what you see a light here.
That's because you added salt in it?
Yes, that's because you add salt in it. Yes. Yes, of course, yes. So because of that reason, this is electrolyte. But sugar, it dissolves in water since it doesn't form ions. It is practical. It is really true because it is organic compound. It's not ionic compound. Sugar is not ionic compound, so it doesn't form ions. Right? Since it doesn't form ions, it is non-electrolyte. No ions are there, so no electricity. Okay, so this is for non-electrolyte. Right? Okay. Okay, so, here. Let's do some examples. Write the balanced equation for the reaction with propane, C3H8, with oxygen to form carbon dioxide and water. Okay, let's see how this works. C3H8 plus O8, what are the products? They already gave you the product. Carbon dioxide and water. By the way, what type of reaction is this? If something reacts with oxygen, what do we call it? Well, it's just chemical. It's chemical change. It's chemical reaction. But there is a type of reaction when oxygen is involved. Oxidation is a very common fate, but there is another one, another word. There's a lot of oxidation is like umbrella. It's big. This is called combustion. Combustion reaction. Combustion. C-O-M-B-U-S-T-I-O-N. Right? Combustion reaction. Something reacts with oxygen is called a combustion reaction, and the products are always carbon dioxide and water. Okay? But the point is the equation has to be what? The equation has to be balanced. So that's what we need to make a practice here. Whenever you have a chemical equation, a chemical reaction, that chemical reaction has to be what? Balanced. What is balanced? Katie, what's balanced means? What's balanced means?
Balancing.
Yes. What's balancing the equation means? Balancing means that how many atoms you have on this side, you need to have the same on the product side, right? So if I have 8 hydrogen here, how many hydrogen I need to have?
8.
So to do 8, how many hydrogen I need? 4. I put 4 here in front of H2O. Okay. How about carbon? I have 3 carbon here. So what do I do? Where?
On the right side, multiply it.
Where? Here?
3.
Underneath of carbon?
In
In front. Very good. In front. In front of CO2. The coefficient. The coefficient. Please remember, the coefficient is always the one we have to. Yes.
Can you repeat that? What you said?
Okay. Okay. When we balance the equation right here, okay, when we balance the equation, let's say I have 3 carbon here, right? I need to put 3 here in front of the carbon dioxide to balance. Balance means how many atoms I have on the reactant side. I need to know the same amount on the product side. Okay? Always I use the coefficient. So, for example, I have 8 hydrogen here. Look, I have 8 hydrogen here. How many hydrogen I need to have to make it 8? Actually, I put 4 here. Yes, because 4 multiplied by 2 gives me 8. 4 multiplied by 2 gives me 8, you see? Now,
But then, isn't it 4 oxygens?
yeah, I have 4 oxygen, you're right, and I also have 3 oxygen. I mean, I have 6 oxygen. 6 plus 8 is going to be 14.
On
No.
the other side is.
Let's see, okay, let's see. Okay, so this is going to explain us clearly, okay? You see, you put 3 carbon on the left, you put 3 here, right? You're going to put, to make this 8, you're going to put 4 here, right? That makes 8. But how many oxygen you have on the product side? Altogether?
10.
6 plus.
Yes,
10.
10, yeah. 10, yeah. We have 10 oxygen on the product side. You agree with me?
Yes.
Okay.
So you have to add put 5 over there.
So what do? I'm going to put 5 here. Do you agree with me?
Yes.
How do you got 10 oxygen?
Because 6 oxygen here, plus 4 oxygen here, together, this is product. On the product side, I have 10 oxygen. I have 6 here, I have 4 here. No, go ahead, yeah.
I'm not seeing how you have 10 oxygen over there.
Look at it. These 3 is for carbon and for oxygen, right?
Carbon and oxygen.
Yes, yes, this is a coefficient that's used for carbon and for oxygen. So I have 3 carbon, and how many oxygen I have here on carbon dioxide? 2 times 3, that's 6. Is that what you're saying?
Now I got it.
How many oxygen I have here? 4. Now, all together on the product side, how many oxygen I have on the product side? Product means this is product right here.
So you have 10.
I have 10 altogether. I have 10 oxygen. Yes? No?
No.
No?
I'm
Okay.
like 4 times, you said, don't you do 4 times 2?
Yeah, that's
Yes?
Well, that's
3 times
That's for the hydrogen, that's not for the actual oxygen.
Oh,
Oxygen has 1 on the bottom, so it's 4 times 1.
alright, gotcha.
But
Make
then,
sense?
it's
Yeah.
not even that.
Yes, it's not
You
even.
still have
Yeah.
6.
So we have to make balance that. We have 10 oxygen here. So what do? You have to put a number.
5.
You have to put 5. You have to put 5 here. Okay, maybe the next step can tell you that. See, press 5 to balance oxygen. Now the equation is balanced. Yes? No? Actually, balancing the equation really doesn't have a role, to be honest with you. Balancing the equation is a trial and error method. I put 2 here, and now see, I change the number, and I can go back and forth. Okay? Back and forth. There is no a specific rule for balancing the equation. It's depending what type of chemical reaction I have. Okay? It's like I see 3, okay, let me put 3 on this side. If it doesn't work, then I can change the number. Okay?
What's the whole kind of balancing? Is that just to make you steady, or?
Okay, who can answer? That's a very good question. What is the whole point of balancing the equation, really? What do we need? Why we need to balance the equation? That's a very good question. How do you interpret that? What is the purpose of balancing the equation, Kate?
Because, for instance, what you do with salt and water,
Mm-hmm.
like there are maybe 5 grams of salt added with water. You can have 2 grams at the end of everything, like if you have to separate the salt and the water. I don't know if I'm explaining it right. Like you have 1 gram of water and 1 gram of salt. You mix them together, at the end of everything you should have 2 grams.
2 grams, yes.
Which is 1 gram of salt and 1 gram of water.
What law justifies that?
Conservation of energy?
Yeah, conservation of mass.
Conservation of energy.
You know, there's a theory that says matter neither created nor destroyed. What does that mean? Matter never been created nor destroyed. Nothing is lost, right? And whatever we have is there, was there, right? It changes. Its chemical composition is changing, of course, but in terms of quantity, it has to remain the same. Now, as a chemist, how do you show that? You have to balance the equation. You need to balance the chemical equation to indicate how many atoms you have at the beginning, how many atoms you have at the end.
So kind of what you're saying is like whenever you put salt in the water with it breaking down and everything, you have, and whenever you test it, you only get part of it. So then that's how you have to balance it from the original to what it is now.
Yes, yes,
Okay.
yes. Theoretically, whatever you started with, you need to get the same amount. But
Right.
practically, experimentally, that's not true. We always get less.
Right.
But the concept is the equation has to be balanced. At least we get 99% of our products get back. Okay? There is spilling, there is really some things will be absorbed, but the amount pretty much has to be remain the same. So to report that, I have to balance the equation. That's the purpose of balancing the equation. Okay? Okay, now there is something called a mole. A mole is a quantity that contains 6.02 times 10 to the power of 23 atoms. Okay, are you familiar with these numbers? How many of you heard these numbers and what does it mean? 6.02 times 10 to the power of 23. What do you call this number?
Scientific notation.
Yeah, it's a scientific notation. It's written in a scientific notation, that's true, but behind scientific notation there is something secret in it. What is that? I'm sorry? It's a big, big number. Okay, let me give you an example. When you go to the shop, when you go to the store, you buy a dozen of eggs. Normally, you buy a dozen of eggs. How many eggs are there? 12. Are you counting them? No.
I usually look at them.
Yeah, because it's dozen. If it's anything is dozen, it's 12.
Well,
I mean, common sense. We all have an understanding. A case of something, one case, a case of soda, for example, has 24, right? Case of water, maybe 24. This is a number that we use in our daily life, right? Now, atoms, molecules, particles, they are very smaller things. We can't see them in our eyes, okay? If you have this water, this is full. Like if you have 5 or 6 milliliters of water, in 5 or 6 milliliters of water, there is billion molecules of water. Like this size water, there is a billion number of molecules of water out there. You can look that with special kinds of instruments, some kinds of mass spectrometer. You can have a million number of molecules. How do you count them? It's very hard to track the numbers, just a little bit. Let alone this full of water. This full of water has trillion number of molecules of water. 100 trillion, 200 trillion, or 500 trillion molecules. Because, you know, just imagine, you have a smaller, atoms cannot be seen, cannot be observed by our eyes. But you see the water, right? So matter is basically made from atoms, particles, right? If you can see them, if you can see the water, you can imagine that billion number of molecules of water are here because you see them. That's a combination. The combination of all these molecules of water makes us see in our physical eyes. So, just like one case is 24, just like 1 dozen is 12, right? Chemists came up with a number to count the number of atoms. That is 1 mole. And there is an Italian scientist who developed this and introduced to the scientific community first. That is like he didn't like dream this, so he did experiment and he found out that 1 mole of any substance has 6.02 times 10 to the power of 23 particles in it. 1 mole of anything. 1 mole of anything. Just like 1 case has 24, just like 1 dozen of egg has 12, 1 mole has this much number. And this number is called Avogadro's number. Avogadro's number. Avogadro is an Italian scientist. It is in pride of his name, in respect of his name. That was his ideas first, and it's accepted by many experimenters, by scientific communities as well. So now, like, what is 1 mole of water equals to? No, in terms of gram. In terms of gram. This is in terms of molecule. 1 mole of water equals to how many grams? 18 grams. 1 mole of water is 18 grams. 1 mole of water is 18 grams. How do I come up with that number? How do I come up with 18 grams? No. I take the atomic weight of hydrogen plus I take the atomic weight of oxygen. Water is made from H2O, right?
So what is it, what of water?
1 mole of water.
Spell it.
1 mole. M-O-L-E, right here.
M-O-L-E?
Yeah,
Okay.
I'm talking about mole, right here. I'm
I
trying
wanted to
to...
make sure I was hearing you right.
Okay. 1 mole is 1 mole of water. 1 mole of water, in terms of gram, is 18 grams. Do you agree with me? Huh? 18 because H2O. H2O is 2 atoms of hydrogen plus 1 atom of oxygen. H2O, right? The atomic weight of hydrogen is 1 gram, right? And the atomic weight of oxygen is 16 grams, right?
Yeah.
So if you add them, 1 mole of water is how many grams?
17. So you say 18.
No, we have 2 molecules of 1.
It's
Oh,
18.
2. Oh, you got
It's
hydrogen,
18.
hydrogen, so-
H2O.
I don't get it.
I
got 7.
Really? Okay.
I really don't. I just don't you doing.
We're using the math.
Okay. 1 mole of H2O, right, equals to 2 times 1, which is the atomic weight of hydrogen, plus 1 times 16, because there's 1 oxygen, which is H2O, right? Right? Do you agree with me?
Yeah.
That means this gives me 18 grams, right?
Oh, because the atomic weight of
Water
oxygen
and
is
hydrogen plus.
15.9.
Oh, you're doing like the math. Okay, okay.
Well, 15.99, we can round it to 16 to, I mean, it's pretty much 16. Okay. Okay, do we agree with this? Now, let me ask you another simple question. Can you, if I ask you in the lab, right, I need 18 grams of water. Can you measure 18 grams of water for me in the lab? Let's assume we are in the chemistry lab right now. I need 18 grams of water. How do you do that? No, experiment. No, we're not doing calculation. I need 18 grams of water. Huh? Guess what? How do you measure it? Tell me that. How do you measure it? Okay, tell me. I need the steps.
Put water in the cylinder.
Okay, put water in a cylinder is volume.
Yeah, but then you can put it on the scale and measure it with a gram.
Okay, so you have to first find out the measure of the weight of the
Cylinder.
the weight of the cylinder,
Right.
right?
So you can take it with
You can vary that, subtract that,
Yeah.
and then you can put the water till you get 18 grams. It's simple, right? It's very easy. It doesn't really, it's not complicated, right?
But if 1 mole is that small, how can we measure it?
Well, 1 mole, there's a difference between 18 AMU versus with 18 grams. Okay. What's AMU? What's AMU? mass unit. Atomic mass unit. 1 atomic mass unit equals to 1.67 times 10 to the power of what? Minus 24 grams. That's how the weight of the atoms are. 1.67 times 10 to the power of minus 24. Imagine how smaller they are. That means it is 1 AMU means 0. What? 0, 0, 0, 0, 0, 0.
Lots of zeros.
A lot of zeros.
167.
167 grams. It's very small. It's really very, very small number. And the numbers, these numbers, the atomic weights that are listed in a periodic table are in AMU. We need to have a special type of instrument to measure atoms in terms of AMU, like mass spectrometer, for example. But you convert that idea, instead of AMU, you use what? Grams. We can do grams here in our chemistry lab, right? We have a top loading balance, we have a scale, and we can do grams. 18 grams.
So
Now,
how big is 18 grams of water?
18 grams of water.
How big is it?
That's, I don't know how big it is, but it is 1 mole of water.
And
18
this is
grams.
more than 1 mole, right?
How do I know? I don't know. How do I know that? How we have to measure it? It should be.
I want to have an idea of what you're trying to
It should
say.
be. It should be. Maybe it's a little bit more than that. It's a little bit more than that. That would be 18 grams.
Okay.
Okay, let me. Okay, forget the liquid. Forget the liquid. Okay, sodium chloride, salt, common salt, right? Can you measure? Okay, let me ask you this. I need 58.5 grams of sodium chloride. How do you do that? Tell me the step, the whole step. I need 58.5 grams of sodium chloride. Okay, what you need to do is you use a scale. Maybe you use evaporating dish or something to put that 58.5 grams, right? You take away the weight of that evaporating dish. Yes, and then add with a spoon sodium chloride till you get what? Till you get 58.5 grams. That is 58.5 grams, right? That is 1 mole of sodium chloride. Yeah, because that is 1 mole of sodium chloride equals to 58.5 grams because sodium has 23 grams. Yes, chlorine has 35.5 grams. That gives you 58.5 grams. Alright?
But we got this on a test, would you give us those numbers?
So, yeah. These numbers will be given. These numbers will be given on the test. These numbers will be given. But what I'm trying to relate
Okay, so I
is,
think I'm confused. How big is 1 mole? I think that's what I'm saying. How big is 1 mole? Because with all these figures, it looks
in
like
terms
1
of
mole
grams,
is very, very small.
It depends on what substance it is.
like 1 mole of sodium chloride is 58.5 grams. 1 mole of water is 18 grams. 1 mole of potassium chloride will be the weight of potassium plus the weight of chlorine.
You don't need to factor in that 6.02.
I'm coming to that. Now the point is, as far as it is 1 mole, it has 6.02 times 10 to the power of 23 molecules are here. You see, I'm indirectly measuring the number of molecules in 18 grams of water. I don't see them. I can't see them. There is no way for me to observe, to see by using physical naked eyes. But having 18 grams of water guarantees me that I have 6.02 times 10 to the power of 23 molecules of water. Having 58.5 grams of sodium chloride, it guarantees me that I have 6.02 times 10 to the power of 23 particles of NaCl. Why definition? Because according to 1 mole, anything is 1 mole has this number.
Water, whose molecules and atoms.
Depending on what you're measuring. If you're measuring water, you're talking about molecules. If you're measuring like ionic compound, you're talking about particles, yeah. Or if you're measuring a single atom, you said one atom, yeah. Yeah.
That whole long thing.
Yes, yes. Well, I will tell you a little bit different thing. If I have 28 grams of water, how many molecules of water I have?
Like 1.9.
6.
Oh, 9.
Say that again.
If I have 28 grams of water, and I need to count the number of molecules of water.
You have 6.02 times 10 to the
28 divided by 18.
I don't know.
It'd be 28 divided by 18.
It's 28 divided by 18, yes. Why? Okay, write this down. We have 28 grams of water, example. And we wanted to know how many molecules of water we have in 28 grams of water. How many molecules? Yes.
It's 28,
28 divided by
28 multiplied by this number, the number.
Molecules of water are in 28 grams of water. How many molecules of water we have in 28 grams of water? Okay. It's very hard to answer the question just if you look at these things, right? But we know the fact here. If it is 1 mole has how many grams? 18 grams. In 18 grams, how many molecules you have? What is that?
6.02 times
6.02 times 10 to the power of 26. So that's 1 mole though. That's 1 mole.
Oh, so.
That is 18 grams. But I'm asking you 28 grams. Do you expect more molecules or do you expect less molecules?
More molecules.
Obviously, you expect more because 18 grams of water has 6.02 times 10 to the power of 23. 18 grams. If I have 28 grams, then it has to be more than 6.02. Obviously, right? So, how do I do this? I would say, okay, you know what? First of all, 1 mole of H2O equals to 18 grams of H2O. Do we agree with this?
Yes.
If I have 28 grams, how many moles we have?
1 point something.
Yes.
I don't have a calculator.
Yeah, okay, you can use a calculator. We use conversion factor.
28 divided by 18.
Yes, 28 divided by 18. That means 28 grams times 1 mole over 18 grams.
1.55,
1.56. 1.56 what?
Moles.
Moles. This is more.
So you do the 1.56 times 6.02 times 10 to the
That's correct. Yes, yes. Because 1 mole has 6.02 times 10 to the power of 23. The 1.56 has how many molecules?
1.56 times.
1.56 times 6.02 times 10 to the power of 23. 1.56 times 6.02 times 10 to the power of 23. Okay? It says here, 1 mole of carbon atom, for example, has 6.02 times 10 to the power of 23 carbon atoms. 1 mole of water has 6.02 times 10 to the power of 23 water molecules. As far as this 1 mole, it always have the same number.
It's always 6.02 times.
As far as this 1 mole, yes. Just like it's always, just like 1 dozen. It doesn't matter. 1 dozen egg, 1 dozen pencil, 1 dozen whatever. Okay?
And that always needs to be in the answer, that equation.
Like what? Like what?
Like if you write this for 1.56.
Well, for example, if my question was, I pick a number, I just pick 28 grams of water. And I wanted to know how many moles I have in 28 grams of water. Okay, this is my question to you. So,
You would have to know how many, 1 mole.
1 mole of water, yeah, in order to answer that, you need to know what is 1 mole of water will be equivalent to. Okay, then you have to convert the gram to moles. You have to convert the gram to moles. and then multiply by the Avogadro's number by 6.02 times 10 to the power of 23. Okay? So the number 6.02 times 10 to the power of 23 is Avogadro's number, and it can be used as a conversion factor to relate the number of moles of a substance to the number of atoms or molecules, you know. So 1 mole over 6.02 times 10 to the power of 23 right here, or 6.02 times 10 to the power of 23 over 1 mole. You can do vice versa actually. You can do vice versa. Okay, that's a very good question. How many molecules are contained in 5 moles of carbon dioxide? What do you think? How do you answer this? Let's say we have a test now. Yes.
You gotta know how many, you gotta find
Carbon has 12.
and then oxygen and.
Oxygen has 16. So what is 1 mole of CO2 would be equal to?
44.
What do you say, Kayla? 44. 1 mole of carbon dioxide is equal to 44 grams. Is everybody okay with that? How many of you got 44? 44 because carbon is 12, oxygen is 16. But we have 2 oxygen,
Yeah.
16 times 2
32
plus 12. Yes. Okay? That's 44. Make sense? So, carbon is this from the periodic table. The atomic weight of carbon is 12, and the atomic weight of oxygen is 16. So,
we leave it 44 times 5.
Yeah.
wait a minute. Wait. I'm asking you one more of. Try to understand the question. Read the question first, okay?
Oh, molecules.
How many molecules are there?
Oh, 5 times 44 times 6.
Oh, that'd be 5 times 6.2 times 10.3. Those molecules, right?
Yes.
Yeah.
Yes. So the answer would be what?
5 times 6.02 times 10 to the power of 23.
Yes.
That was dumb.
Yes. The question is 1 mole of carbon dioxide equals to 6.02 times 10 to the power of 23, right?
Right.
As far as it's 1 mole. If you have 5 moles, then 5 times 6.02 times 10 to the power of 23. Right?
Right.
5 times 6.02 times 10 to the power of 23 moles. So we have 2 choices. Write out the conversion factors. So 1 mole equals 6.02 times 10 to the power of 23. And 5 moles is going to be 5 times 6.02 times 10 to the power of 23.
Oh, so it doesn't have to, you don't have to look for
The mass, you don't have to know.
No.
Mass. We're
No.
looking for the molecules.
No, we don't need that. Does that make sense?
Yeah.
Okay. Thank you. 1 over, right? Okay. So, you just multiply 5 by 6.02 and you come up with 3.0 times 10 to the power of 23. Is it big or less?
Big.
Bigger.
It's bigger. 3.0 times 10 to the power of 23 is much bigger than 6.02 times 10 to the power of 23. Make sense? Yes.
No. I'm good.
Any questions regarding with this?
So you
Okay.
multiply the 5 and the 602.
The 5 by 6.02 times 10 to the power of 23, yes. Because 1 mole of CO2 has 6.02
I
times 10
guess
to
we're
the
gonna
power of
have to
23.
memorize that, huh? 6.02. You keep repeating it. It's giving me,
Impression.
yeah.
Okay. Okay, wait, can we move on?
Yes, sir.
Okay. Now, you see, if you write numbers, if you calculate the atomic weight in terms of gram, we call them molar mass. In other words, let's make this easier. For example, previously I was asking you a question. 1 mole of water is 18 grams, right? 18 grams. 18 grams is the molar mass of water. If I say 1 mole of, if I say 18 mu, 18 mu is not a molar mass. It's going to be what? It is the molecular weight of water, okay? But if you express the number in terms of grams, that is said to be molar mass. So what is the difference between atomic weight and molar mass? Numerically, they are the same. In numbers, they are the same. What's the difference? Units. Molar mass expressed in grams. Molecular weight expressed in AMU. That's all. Which one is very practical for us? Grams. We can do grams in our house. We can do grams in the chemistry lab. It's easy. So expressing weight in grams is said to be molar mass. Molar mass. So here is the question. What is the molar mass of nicotine? And the formula of nicotine is given to you. C10, H14N2. What do you do to calculate the molar mass? We need to determine the number of atoms of each element from the subscripts. How many atoms we have?
3.
3. The number of atoms of each element, Faith.
Oh.
Each element. So carbon has 10.
10 times 14.
Hydrogen has 14. Nitrogen has 2. So that's the number of atoms, right? Once you know the number of atoms, you're going to multiply by their respective atomic weight. Well, actually, you don't have to memorize this. I'll give you the atomic weight during the test, okay? But you need to know how to multiply that. Like, if I have 10, 10 multiplied by what?
10 multiplied by
12 multiplied by 12 for carbon. Hydrogen multiplied by
28.
hydrogen is 1.
Yeah, 1, sorry.
Okay, 1 by 14. Nitrogen,
14.
14 times.
28.
14 times 28, yes. You see here, you are going to multiply the number of atoms of each element by their respective atomic weight and add the results, which means carbon has 10, the atomic weight of carbon is 12.01 AMU. What's AMU? Atomic mass unit. We continue. 14 hydrogen atoms by 1.01 AMU, it gives you this. Nitrogen atoms multiplied by 14.1 gives you 28. Finally, we came up with 162.26 AMU.
You don't want the point there.
I don't want the point,
Okay.
actually. Yeah. Now, here is the thing. Molar mass, as I have said. Molar mass is the mass of 1 mole of any substance reported in grams. Here, is it molar mass? Yes or no? No. Why? Because it's AMU. It's AMU. If it was grams, then we call this molar mass. Okay, we call this molar mass. What is this then? The atomic mass. Okay, it's a molecular weight. But molar mass is a mass in grams of 1 mole of any substance. It has to be reported in grams. In grams.
Professor, what's another name for atomic weight?
I'm sorry?
Another name for atomic weight. I think you said something.
Molecular weight.
Okay.
Molecular weight or formula weight. Now, we use formula weight for ionic compounds. We use molecular weight for molecular compounds. We use atomic weights for atoms. Yes.
Okay, so you take the 162 that we got and multiply it by the 1.67 times 10 negative 24?
Yes,
To get the
yes,
grams?
yes. But Kila, it is really tedious every time you multiply by this huge number. I mean, by this smallest number. So that's why they prefer to write AMU. So the real weight is 166.
So you're not going to ask us to convert the AMU into grams then, right?
No. I understand that if I say AMU, the 1 AMU equals to 1.67 times 10 to the power of minus 24 grams. So,
Okay.
unless I want complicated life.
Right.
But you understand the concept, right?
Right.
Okay. Now, here, let's do this. How many moles are present in 100 grams of aspirin? You have 100 grams of aspirin. And the molecular weight of aspirin, the molar mass of aspirin is given to you. 180.2 grams. So how many moles are there? what do you do? The very first thing, what do you do? If you have a question like this, you need to calculate what is 1 mole of aspirin equals to. Okay? What is 1 mole of aspirin equals to in terms of grams? 1 mole of aspirin. You see, you have to calculate C carbon times 9, 1 times 8, 4 times 16. What do you get? Tell me what do you get. If you multiply 9 by 12 plus 1 times 8 plus 4 times 16. I'm sorry? 180.2. Oh, well, that is what's written, but I want you to calculate that.
You said you
180.
9 times 12,
You said when that.
Professor, 180. Wait, I'm
180. Okay, 9 times 12.
Why is the carbon over at 16?
Carbon is 14. It's not.
Oh, it is 14.
No, carbon is 12.
Right. Why is it 12 instead of 14?
No, carbon is not 14. Carbon is 12.
Like the mass of it?
Yes. Yes, carbon is 12. 12.01 in fact.
Oh. Okay, I see.
Nitrogen is 14.
So each time, so 8 times
8 times 1.
2, 1.
Yes. It gives you 180. It's 180.
Grams per mole.
It's 180. That's 1 more, right?
Yeah.
So
4 times.
1 mole has how many grams?
180.
180. How many moles you have in 100 grams? How do you answer that?
Point
Times
something.
100.
Point
180.
something.
180 divided by 100,
Yeah, yeah, yes. Because we know that 1 mole is 180. Point something, point 2, right?
But you don't
If
want-
I have 100 grams, how many moles I have?
180 divided by 100.
Yes. 100 grams here.
100 divided by 180.
1.8.
Right? So what do you get?
1.8.
If you divide 100 times 1 divided by 180.2, what do you get?
0.5.
Point something.
Well, give me the answer. Give me the accurate answer.
0.56.
0.56 more of aspirin, right? Yes. Yeah, yeah. Yes. 9 times 12, 8 times 1, 4 times 16, that gives you this number right here.
When you add them together.
Yes, 4 times 16 is 64. 8 times 1 is 8. 9 times 12 is 108. So if you add them up, I think you came up with this. Okay? 0.56 mole. Now, another question I would like to ask you. Just relate to that number, 0.56 mole. How many molecules of aspirin are there in 0.56 mole? How would you answer that? How many molecules of aspirin you have in 0.56 mole?
0.56 times 6.02 times 10 to the power of 3.
Yes, yes. You multiply 0.56 by 6.02 times 10 to the power of 23. What is our justification? Where does we get this idea from?
Because 1 mole equals
What number?
6.02.
Yes, 1 mole always equals to 6.02 times 10 to the power of 23. So that's by definition. 1 mole equals 6.02. So 0.56 mole, 0.56 times 6.02, which is less, of course. It's less than 1 mole, and the number of molecules is also less, right? So when we do the calculation, you get 0.555. Okay, we rounded up the number, but we came up with the same answer. Okay?
What was the final?
Okay? Balanced equation, okay. Now, coefficients are used to form more ratios which can serve as a conversion factor. Okay, let's see what examples they have here. Here is a question. Using the balanced chemical equation, how many moles of carbon monoxide, which is CO, produced from 3.5 moles of C2H6? Now, how do we really answer this question, a question of like this? How do we answer a question like this? The very first thing, the equation has to be what? The equation has to be balanced for us. Is the equation is balanced?
No.
Okay.
Yeah, it
Yes,
is.
it
It is.
How many of you say yes? This equation is balanced. Look at the problem and tell me whether the equation is balanced or not.
Yeah.
Those of you who say yes, raise your hand. I have two people in confidence. No. How many of you say no? Okay, raise your hand, don't worry. Don't be scared. Okay. Well, this equation is balanced. Yes, this equation is balanced. How do I know? How many carbon I have?
4.
How many carbon I have? 4 carbon. How many hydrogen I have? 12. How many hydrogen I have? 12. Okay. How many oxygen I have?
10.
How many oxygen I have?
10.
5 times 2, 10. How many oxygen I have?
10.
On the product side, I have 4 oxygen here, I have 6 oxygen here, all together, it gives me 10. So it means that the equation is what? Balanced. No. You have to always compare reactant versus product. Reactant versus product. That's how you need to compare.
So
Yes.
we add the 4.
The 6 and the 4, yes. To get 10 oxygen. Yes. Make sense? Okay. You have 10 oxygen on the reactant side. This is the reactant side, right? How many oxygen you have on the product side? That means the oxygen you have on one of the compound here, the oxygen you have on the other, and you add them up together. That means you have 4 oxygen here plus 6 oxygen here. Because you see, you're going to always compare product versus reactant. Okay? So, if I have 10 oxygen here, I know I have 4 oxygen here, I know I have 6 oxygen here, so altogether, that gives me 10 oxygen. Yes.
I don't get, right there, how do you get 12?
Because the 2 is for carbon and the 2 is for hydrogen.
So which one? 4 times.
This is 2 times 2 is 4,
Yeah.
2 times 6 is 12.
So you add 4 plus 6.
No. Yeah, I'm balancing each element here. How many carbon I have? I have 4 carbon. I have 4 carbon. How many hydrogen I have? I have 12 hydrogen. 2 times 6. I have 12 hydrogen. Okay. Right? Okay, let's move on.
Sir, excuse me.
Yes.
In the printout, it's
Yes.
not balanced. The oxygen is not balanced, but there it's balanced.
Oh, well, I don't know about that. But thank you very much for reminding me. But now we balance it, right?
Yeah.
So you like this?
That's why I said
That's why
it's not
some-
in balance, because I was looking at the PowerPoint, not
Uh-huh. But I don't know, makes us PowerPoint. That's by the book owners, they just made it.
Yeah, but we're
Okay, but they balanced it for us, right? Now, here is the thing, I want you to understand that balancing the equation is not just like a game. It's not like because we like it. It's not because of that. Because of balancing the equation, we apply that, we're going to use to interpret how much carbon monoxide, which is this mole of carbon monoxide, is produced if I have a given amount of C2H6 or ethane. Let me interpret this, what it means, stereochemically or in terms of chemistry. What this means is every 2 moles of C2H6 can guarantee you, can produce 4 moles of carbon monoxide. It's like proportional. If I have 2 moles of this, I guarantee you, I get you 4 moles of carbon monoxide.
Okay, and then the same thing with the second one, if you have
Same
502.
thing, if I have 502,
6H2O.
I will get 4CO or 6CO. If I have 10O2 instead of 5, how many you get?
You get twice as much.
We don't know.
20.
We don't know. You have to make comparison. Now, that is the thing I want you to be careful really.
Okay, you have, yes.
Yes. If I have 5 moles of oxygen, how many moles of carbon dioxide I get? According to that, 4 moles of carbon dioxide. I double this. 10 moles of oxygen. How many moles of carbon dioxide I get? X. No.
You have to balance.
Yes. You have this crisscross. Not double. Not always double. Okay. So this is going to be.
Why are you only taking part of the equation?
We have
I'm just giving you an example.
Okay, so you're still
I'm just
keeping
giving,
it.
yes, I'm just trying to show you the interpretation, what it means. Balancing the equation is not because we lie, but there is a big significance behind that equation. Really, there's a big significance. The basic concept of balancing equation is actually, we wanted to know how much the products that we get from the reactants. It is like, economically, it is very much significant to tell. Or let's say that you're working in a chemistry laboratory and you wanted to tell your supervisor or the owners or whoever is in charge of that, you know, you have to spend about this much propane or ethane in order for you to get this much product. You really give them that information, okay? Sometimes you wanted to clean water, a big water tank, water reservoir, and you wanted to avoid or you wanted to eliminate the contaminants there. And they will ask you to add chemicals in it, okay? So how many chemicals you add and how many product you get is based on balancing the equation. If you ask less, you're not going to clean up all the water reservoir, the contaminants of the water reservoir. If you ask more, you will really unfriendly to the water reservoir because you are creating some unwanted precipitation, unwanted materials. You are not removing the contamination, you are creating contamination. Okay? Let's say, for example, in the water reservoir, they use if I don't make any mistakes, they use aluminum sulfate to remove the phosphate, to remove the bacteria, to remove the other materials. How much aluminum sulfate I'm going to add in the water reservoir is equation, it's a chemical equation. Okay? So you have to be, that is how balancing the equation is really, really needed. So let's, for example, let's, here.
Professor, is it the same thing as you have 2 molecules of hydrogen and 1 molecule of oxygen gives you water?
2
Or
molecules.
3 molecules of hydrogen
Yes.
and 2
Yes.
molecules
Yes.
of oxygen.
This gives you how many molecules of water?
Like hydrogen, 2 molecules. Is it 2 molecules? H2O.
Like you want hydrogen plus oxygen gives me H2O and it is 2. Yes, go ahead.
No, not 2. Take out the 2. Take out the 2.
Where, here?
Yeah, on both sides.
Okay.
But H3
H3.
H3.
Where H3? Where do I get H3?
I'm just saying, I'm trying
You
to.
want me to write H3 here?
Yes.
Okay.
It doesn't give you water. Is that what you're trying to say?
Yes. First of all, wait, the H3, that's the H3.
Yeah, I know.
Okay. So, yeah, let's discuss with the things that existed. I never saw H3.
I'm asking you a question. Like, it has to be H2 to be water, right?
Yes.
If it's not H2, it's not water.
If it's not H3, it's not water. Yes, it's something else. It may be
So that's
hydrogen.
advancing the equation,
Yes,
right?
yes.
Also, you can examine the composition of the product that is formed.
From hydrogen and oxygen, you may not always get water. You may get hydrogen peroxide. Hydrogen peroxide is H2O2. We have still 20 minutes.
No attention.
10 minutes. We have 10 minutes. Let me finish because it's very important here. You know, when I say it's very important, it's going to be on the test.
Test next week, but we get.
No, this time not next week. This time is going to be a week after. But this question, you should expect that this is really.
So you're gonna give us a review this time?
Okay, let's first understand this. Let's first understand this, okay? I'm trying here that to explain it to make sure that you understand here, okay? Let's first understand this, and then we'll discuss about the latter, okay? Let me start here. So now let me go here. If I have 5 moles of oxygen, I have 4 moles of carbon monoxide. That is a guarantee. Every 5 moles of oxygen provides me how many moles of oxygen? 4. Let's say if I have 10 moles of oxygen, how many carbon monoxide I get? X. So what is X? Crisscross, if you want to. So X will be 10 times 4 divided by 5, right? 8. I got 8. Okay? I double it. Well, this time it is proportion. 5 moles of oxygen gives me 4. If I have 10, if I make it twice, then it's going to be twice, which is, if this is 10, this is going to be 8, right? If this is 25, this is going to be maybe, we multiply that.
Professor, if that is 10, this will be 8. What about the
What about that?
Which one?
What?
We can calculate that.
So,
We can, what do you think?
so we cannot just only change
No, no,
the
no.
form.
No,
We have
no.
to change the water.
Yes,
Yeah.
yes. It's not only changing the carbon monoxide, it's also changing the water. Yeah. This is a chemical reaction. I'm just speaking carbon monoxide. But, when this is changing, yes, this is also changing still. Okay? Now, let's pay attention here.
So if you change that, so then we have to go back to the other side to CO2 and we have to change that. So we changing the whole.
Yes, everything is related here. I'm just isolating this case here, but everything has to be changed. Everything has to be changed. But now, let's go here. The idea is that every 2 moles of C2H6 generates how many moles of carbon monoxide? 4. Every 2 moles, according to the equation, every 2 moles of C2H6 gives me 4. Now, this guy gives me a little bit different number. 3.5 moles of what? C2H6. How many moles of carbon monoxide I would get? Just the same way. Every 2 moles of C2H6 provides me how many moles of carbon monoxide? 4 moles of carbon monoxide. If I have 3.5 moles of C2H6, how many moles I get? X. So X would be 3.5 times 4 divided by 2, which gives me what? No. 7. 7 moles of carbon monoxide. Right? Every 2 moles of C2H6 provides how many moles of carbon monoxide? 4. They wanted to know what is the question? The question is how many moles of carbon monoxide we get if we have 3.5 moles of C2H6. So I make a comparison. 2 moles of C2H6 provides me 4 moles of carbon monoxide. If I have 3.5, it gives me X. Then I use what? I use crisscross. 3.5 by 4 divided by 2 to get the unknown.
So it's 3.5 times 4 divided by
2.
Okay, so you have 2 from there.
Yes. So that gives me 7 moles of carbon monoxide.
So
Right.
this is a question. Can we also do like 3.5 moles C2H6 and then with the water do the same thing we have to
You
do?
can, yeah.
So you have 2 answers then for that instead of only
Well,
7.
certainly, the point is here. I ask you carbon monoxide, I didn't ask you water. Now let's change the venue. Let's change that. I don't want carbon
whatever
monoxide.
Yes.
Do you understand? I would say, you know, this time I need water.
Okay.
Okay.
So that formula would be.
Yeah, the principle is the same. The principle is the same.
Yeah.
Do we understand? Everybody?
Write it over. Okay.
Over
I didn't
2.
see that zero.
3.5 times 4 over 2.
Where you get to?
From here? Okay. Okay. How many of you understood it? Okay. Okay. Let me ask you this. We have 5 minutes. Let's see. Let's just make a practice. Okay.
Just change that CO to H2.
No, we use this equation right here. Here is my question for you. Based on this equation, the equation is balanced for you. Everything is balanced. You don't need to balance the equation. How many moles of water? How many moles of water are produced if I have 8 grams of oxygen? Write this down, please. How many moles of water are produced if I have 8 grams of oxygen? Okay? Based on this equation, I want you to tell me how many moles of water are produced from 8 grams of oxygen. Let's see how you approach this problem. 6 H2O, yes. So now the comparison is between what and what?
Oxygen and.
Oxygen and water. Oxygen and water. Okay? The comparison is between oxygen and water. So what you need to say is, okay, 5 moles of 5 moles of oxygen provides me 6 what?
H2O.
6 what? 6 moles of H2O. 6 moles. Every 5 moles of oxygen provides me 6 moles of H2O. That is the starting point, right? So what did I give you? I gave you 8. 8 moles of oxygen. Gives me how many moles of water?
X.
X. So you use what?
So 8 times 4 over 5x.
I'm sorry?
8 times 6.
8 times
8 times 6.
Oh, sorry.
8 times 6 divided by? 8 times 6 divided by 5. Yes, what do you get?
9.6.
9.3. Okay, and I have a witness.
9.6.
9.3.
9.6.
It should be 9.6.
9.6.
9.6. Okay, 2 people got the same answer. You got it? 9.6?
That's 9.6.
9.04.
It's 9.6.
Okay, good. What you need to do, again, how many of you got 9.6?
Don't nobody say nothing different.
What we can do is we always go with our equation here, okay? The equation tells me that 5 moles of oxygen provides me 6 moles of H2O. What did I give you?
8
If I have 8 moles of oxygen,
equals X.
X,
Cross multiply.
X moles of water, right? So X would be 8 times 6 divided by 5. You get 9.6 moles of what? Water, right? Now, let's add one more point here. Instead of moles of water, because things are measured not in moles in real life, things are measured in grams. Yes. Now, your supervisor wanted to get the answer, I don't want you to give me moles. I want you to give me the answer in grams. So how many grams of water I would get? Or how many kilograms of water I would get? What do you do?
9.6 times 1.06.
No, how many grams? I didn't say how many molecules. How many grams of water? Real grams, 10 grams, 100 grams. What do you do?
That's not good.
9.6 mole of water times what? 18. 18 grams.
Why did you have to?
Because 1 mole of water is 18 grams. I need grams.
Oh, because we're converting that to the water.
Yes.
Okay.
So what do you get? 9.6 by 18, what do you get?
172.
I'm sorry?
172.8.
172.8 grams. H2O, yes. Okay. How many kilograms of water I need? Divided by 1,000.
Divided by 1,000.
Divided by 1,000, right? They want the answer. Once I have grams of water, I can say, well, if they want the answer in kilogram, 172.8 divided by 1,000. That gives me kilogram of water. See, we have a lot of options, a lot of opportunities once we understand converting moles and relating moles of the reactant to moles of the product. We're going to continue on next week. Please read.
Are we good then?
What's
our midterm on?
We don't have a midterm per se. Every time you will be given exams, so we don't have a midterm.